Perfect. I'm Ramnandan. I'm a software engineer and a product growth ninja in Cosmos DB. So two hats. On the product growth side, we deeply engage with customers to understand their pain points and identify opportunities where they can leverage Cosmos DB and make them successful. And as a direct result of that, we basically bring back a lot of feature requirements and then work on those features. So in that regards, I help build the bulk ingestion functionality as well as the native Spark integration for Cosmos DB, which we'll talk about today. And please do tweet. We're very active. The entire Cosmos DB team is very active on Twitter. So do send your questions and feedback even about this session. Tweet. My handle is right there, and you can also, and that's my email address if you want to follow up with questions later on. And the picture is not just a show of how bad I am at photo editing, but just that other than when I'm helping grow Cosmos DB, I really love traveling as well. So how many of you here are using Cosmos DB in production or in your business today? A good amount of you. So thank you. You're the reason we are the fastest growing Azure data service today. So just a quick, there is a lot to talk about Cosmos DB in itself, and I have a 75-minute session tomorrow at 10:30 in the morning. So please do come for that if you want to learn more about design patterns on Cosmos DB. But today we want to focus more on just how do you build scalable IoT or real-time event-driven architectures using Cosmos DB. And for that, I think it's important to just give a primer. Cosmos DB is really good at three things. One is partitioning, replication, and resource governance. So partitioning, Cosmos DB is a horizontally distributed database. And what that allows us to do is give you elastic scalability in storage and throughput. We really put no restrictions on the amount of data and throughput you can expect out of the database. As you throw more data at us, we stand up additional shards to house that data. And for a lot of our e-commerce customers, for example, on Black Friday, their footfall goes up by 10x, and automatically, with just a click of a button, they can provision 10x or 20x more throughput on Cosmos DB. The other is global replication. Cosmos DB is a born-in-the-cloud database. What that allows us is to take advantage of the entire Azure infrastructure. We are a Ring 0 service, which means every time a new data center comes up in Azure, Cosmos DB and the service is immediately up within a few minutes. And this now allows you to think about global replication as just a click of a button to basically replicate your data to wherever your users are. And the last and the most important thing is resource governance. Unlike other databases, where even distributed databases, where you are given a dedicated cluster, which is really good, but when it comes to the total cost of ownership, when you have a dedicated instance or a dedicated cluster, you really cannot amortize the cost and come up with what is an operating cost per every new user I add. Versus with Cosmos DB, we've built multi-tenancy right in. It's really built into the database system where we have hundreds of customer accounts who run on a cluster of machines. And when we do that, basically, and we do that because we translate the cogs back to you in terms of Cosmos DB is really cheap compared to other distributed database systems. But that brings about a fundamental problem, which is how do I ensure that if I have an Adobe or a Walmart running on the same cluster of machines as where you are running, and say there is Black Friday. Now there's one, Jet.com has provisioned 1 trillion RUs. How do I ensure that you and your account does not have negative side effects of that? That is essentially what resource governance is. And that essentially allows us to give those comprehensive SLAs, not just on latency, but also on availability, consistency, and throughput. So Cosmos DB, we are really proud to say that today we have SLA guarantees for latency for both reads and writes, which are less in the single-digit range at the 99th percentile. So let's switch back into what the focus of today's talk, which is building real-time IoT pipelines, right? And IoT pipelines, essentially, you can extend that to the concept of building reactive paradigms or event-driven architectures. So these are some of the examples of event-driven architectures. IoT telemetry processing, as you can see, Walmart uses us for their heating, ventilation, air conditioning architectures. And then you have Toyota, Mojayo, which are using us for vehicle telemetry. You have building automation systems, Schneider, Honeywell. And then you have e-commerce, order processing. You have real-time financial data processing. So underlying all of these is essentially the paradigm of building event-driven architectures. So why do customers think about Cosmos DB when you're building an event-driven architecture? It's because when you're building any microservice architecture even, you expect a high volume of database writes and your database to be able to handle the large volume of database writes. And that's where Cosmos DB being a write-optimized database, we have no concept of locks or latches, which makes it really suitable for massive ingestion rates. And then comes the elastic scalability of storage and throughput as well. So today, when you have a huge spike in the amount of sensor data and IoT data which is being sent out, you really cannot place a restriction of my database can only hold 4 terabytes of data. Because as your data grows, we automatically out and we handle the entire partition management and everything transparently. You don't know anything and there is no downtime even for you. And the last thing is, so if you're familiar with building IoT pipelines, you know that there is, other than a database, you also need a partitioned and a distributed log, which is where things like Kafka event hubs come in. So what differentiates Cosmos DB as a database is that we just don't provide you the database functionalities such as point lookups and point writes and query capabilities, but we also expose a partitioned log interface to the database. What that essentially allows you is, so that's basically what change speed is. So imagine if I had to, I have a stream of IoT data coming into the database, and now I have to get a stream of the events in the same order in which they were ingested into the database. I could use, basically issue a query where I could order by the timestamp. But that's basically now becoming a query, and it essentially is going to cost you a lot of RUs as well. And RU is the concept of, is the kind of the database currency we have in Cosmos DB. So rather than doing that, which is more expensive, Cosmos DB, basically we implement a partitioned log interface, which is change speed, which is as data is ingested into Cosmos DB, we have a log and a partition log in that, of which contains the events in the same order in which they occurred. And what that allows you is 3 things. One is you can now trigger an API call every time a document is created or updated, and then you can do any downstream processing using Azure Functions, app services, and any other compute service. Or you can now even do real-time stream processing. And we essentially, I have a demo where we'll see some of that, where you can use Azure Stream Analytics, you can use Spark, you can use Storm, you can use basically any real-time stream processing framework. And the last is change speed also allows you now to basically do real-time migrations between different collections. So quick point, which is when you're thinking about building real-time big data processing, right? Not just on Cosmos DB, but in general, what are the requirements you have of this real-time architecture? Which is, my architecture should be able to handle really low latency reads and writes, and they should be able to scale linearly. And they should also be fault tolerant, the entire architecture. So in tomorrow's talk, I basically will be going into a little more detail about Lambda, Kappa, what's the difference, how do we, when should you choose which. But today, basically, we'll focus more on Lambda, which is the superset of basically any big data processing system. In the Lambda architecture, the idea is very simple. As you have a fire hose of data coming into your system, you have 3 components: the batch layer, the speed layer, and the serving layer. The batch layer contains basically a master data set, which is nothing but just your entire historical data, which is just append-only immutable data set. And then you also have so the batch layer contains something called the batch processing framework, where at a periodic frequency, you basically go over your entire historical data, you crunch the data to create an aggregated or a materialized view, which you can now store in a separate NoSQL system for real-time low latency access. And then, so basically, what's the con of this? Which is because your batch process now has to go over your entire historical data. That now means it's not going to be low latency, as well as it's going to be compute heavy. So you cannot run this every second, every microsecond. It has to happen at a rather coarser granularity. And it's probably once a day, once an hour. That's basically based on your business requirement. But what if now I have to also look at data which is coming in that period of time where my data is old? That's where the speed layer comes in, where your stream processing looks at real-time data in a shorter time window, in the last few seconds, in the last few minutes, and it creates a real-time view. So at the end, when you're trying to query your data, you basically combine the results from both your batch view as well as your real-time view. So this is all good. Where Kappa architecture just comes in is when your batch process and your streaming process have very similar functionality, which is where you can club these two together into one single pipeline. But Lambda is essentially a superset of what you can achieve. So before we go into how you can achieve this on Cosmos DB, I want to talk a little more about the native integration we have with Spark. So Spark, as you know, is just a distributed compute engine, which is great because now Cosmos DB is a distributed storage platform. And what we've done is built a native integration between executors or the worker nodes in Spark and the shards or the physical partitions in Cosmos DB. What this now allows you is when you write a distributed program using Spark SQL, we push down the computation down to the database where we utilize the indexes and the horizontal partitioning of Cosmos DB. So rather than, if you have a terabyte of data in Cosmos DB, rather than pulling all of that and doing your processing in memory in Spark, we now push all of that computation down into the database and only retrieve the relevant data back into Spark for processing. So rather than pulling 1 terabyte into Spark, we're pulling back a few gigabytes into Spark. So essentially, it makes your computation more effective, cost-effective, and it's going to be more fast. So this is how you can achieve Lambda with Cosmos DB with lower moving parts, which is instead of, rather than when I have a stream of data coming in, rather than me writing it to both a batch layer as well as a streaming layer, you just write it to a single a raw Cosmos DB collection, and basically using change feed, which we spoke about earlier, you can now listen to the exact changes in the same order in which they occurred and use Spark streaming to do your real-time processing. And using the same Spark infrastructure and the same Spark cluster, you can also perform your batch processing using a batch Spark SQL. So that's the great advantage, which just two moving parts, which is Cosmos DB and Spark, you can achieve the entire Lambda architecture compared to other architectures where you would have a Storm for this streaming processing, Spark for or MapReduce for your batch processing, and a separate database for your HDFS for your raw data, and a NoSQL store for your materialized view. So you can see when you're building such an architecture, there are too many moving parts and there's easy points of failure. But here with Cosmos DB, with just two pieces, you can achieve the entire Lambda architecture. So now let's get to a demo, and basically here I wanted to show a real customer demo. We've abstracted away a lot of the details, but basically it's a building automation system. So today, you know, smart buildings are a really up-and-coming thing today, and essentially each of these buildings have thousands of different types of sensors. You have sensors which measure temperature, which measure CO2 emission, the pressure, whether there is a fuel being or gas being leaked. So essentially in this demo, we essentially will be talking about this architecture here, which is, and what we've done is, let me show you the, basically we've come up with a GitHub sample, which we'll be publicly announcing, publicly releasing today, which essentially will allow you to deploy this entire architecture on Azure in less than 5 minutes with just a single click of a button. We've deployed ARM scripts, CLI scripts to basically deploy each of these instances which are configurable. And let me show you that GitHub repo. Yeah, so this is the GitHub repo, thanks to also my friend from CSC, David, who helped build some of this with me. So I'll probably share this once we release it publicly as well. But what this now allows you is, as you can see here, with just when you run this one single script, you can define all the configurations of Event Hub, the number of worker nodes on Azure Functions, your Cosmos DB throughput, the number of client instances which is going to send sensor data. You just set these parameters, and the script in under 5 minutes would basically deploy all of this on Azure. So this is, for example, one such deployment. So as you can see, the script basically deploys all of these resources under one single resource group. So we have a Cosmos DB instance, a Event Hubs instance, a Functions instance. These are the three things which we'll be going into today. So one other thing which most of you may be familiar with is when you're building out any of these IoT architectures, Locust is a really well-famous load testing framework which will help you to scale up and scale down how much sensor data you're pushing out. So it's basically a framework where you can define what data I'm going to be sending out, and you can also, with just a click of a button, increase or decrease the amount of data you're sending out. So right now we have 2 instances of Locust which are sending data to Azure. Each of these are sending data at around 600 requests per second. And let's look at the data in App Insights. So App Insights has this native integration with Azure Functions, where if you spin up an Azure function, you can see metrics like these. So essentially, as you can look here, you can look at the request rate at which data is being ingested, as well as how much time I'm taking to process each of these requests. So one thing to note here is, and maybe I can show you in Azure Functions, what you can define is the concept of when I'm processing data from Event Hubs, what is the batch size from which I should retrieve from Event Hubs? So right here we have 64, which is the batch size of data which is retrieved from Event Hubs. So when we see here that we're processing 10 batches per second, that's essentially with 4 worker nodes in Azure Functions, we are able to process more than 700 requests per second. And each of these batches completes in under 400 milliseconds, which means each event takes only 5 milliseconds to process. And that's where Cosmos DB's really high ingestion rate and single-digit millisecond latency writes comes in. One other thing is basically in Cosmos DB, as you can see here, we have 2 collections. One is the raw data and then the materialized view. So as I have data coming into Event Hubs, I basically, Azure Functions is responsible for pushing that data into Cosmos DB, and this is the raw data. As you can see, this is basically at every instant of time, every device is sending out a specific value. But now when you're building an end application, you don't want to sift through all of this huge historical data. And that's where what I talked about, the Lambda architecture, comes in. So this you can we'll share these Databricks notebooks as well. So the batch processing is very simple. Because of the native integration between Cosmos DB and Spark, you don't have to write any logic in Spark to retrieve data or write data back into Cosmos DB. So you only have to set up this configuration of which collection I'm hitting. And here you can, for example, in Databricks, you can explore what is my data schema, how does the data look, and what I want to store back in Cosmos DB in the materialized view is an aggregated rollup of, for every device, what is the average CO2 emission, and for every temperature device, what is the average temperature. And this is what, essentially, again, with just one single line of code, you can write a data frame in Spark back into Cosmos DB. And this is what you can see right here in the materialized view. So in the materialized view, what we can see here is for every device, we store what is the average value, what was the last time I stored data at, how many events I've received for the device, all of this into a materialized view. Now what this allows you to do is, in your query layer or in your application, you can now do a point lookup of, for this device, what is the statistics I have. So for example, just one single query of select star from C where this device ID, give me what information I have. So this is a temperature sensor. So as you can see, in just a few milliseconds, you can now identify what are the required statistics. Then comes in the stream processing. Okay, this was great, but I'm running this batch processing every hour. What if I want to look at the events which have happened within the current hour? So that's where the speed layer comes in. So Spark has the concept of Spark structured streaming, which is very similar to Spark SQL you would use in batch layer. So here again, you don't need to write any logic or code of accessing Cosmos DB change speed. All you do is treat Cosmos DB as an event store, and you just write spark.readstream.cosmosdb, and we handle all the logic behind checkpointing and storing or basically distributing the load across multiple executors. All of that is handled within the Spark connector. So here, basically, again, you can define in the stream of data, I basically, again, want to look at what is the average value for my CO2 sensors. And as you can see, this stream is currently running, and the data will be modified in real time. Here we're looking at basically what is the average CO2 emission for different sensors. And one last thing I'll leave you with is talking about the scalability, right? So in the architecture we saw here, we see basically that all data is ingested into this event log, which is event hubs. So the reason why you have event hubs is, so today I have 2 locusts sending data. Now if I spin up 4 locusts instead, which you can basically just do super quickly here. Now I don't need to go and scale up or scale down anything in the architecture which I have which we have deployed now, because the architecture is designed in a way to auto scale. So what that means is, even though I've doubled the scale of events which I'm pushing into the Azure architecture, event hubs basically automatically scales to ingest that data, and the rest of the system really does not get affected. Function still has 4 worker nodes which is processing data at the same rate. Now what you can do if you want to double the processing rate is go to Azure Functions, and basically, so if you look at Azure Functions here, it shows you, so here you can see you have 4 servers online. Rather than 4 servers, if I do 8 servers, I can basically go from processing 500 events per second to 1,000 events per second. But it's basically just that, and there is no other additional code change or config change which you now need to do to scale your real-time architecture. So that's basically what we wanted to show here, and I really encourage you to attend tomorrow's session on advanced Cosmos DB design patterns and architectures, to go a little more in detail, because that's a 75-minute session compared to this 20-minute session. So thank you very much.